Okay, so I'm going to give an introduction to high-dimensional expanders. My plan is to, so it's a kind of a relatively new topic. I've been interested in it for the past 3 years and or so, and I think it's very exciting. I think it has to do with a lot of different areas. For me, I was interested in it because it seems to be related to PCPs. But today, I won't talk about those things. I just want to give you 2 definitions for high-dimensional expanders that will coincide, so they will be equivalent. And so give the definition, slowly prove the equivalence, and see what kind of things we can do with them. So the first definition will be the definition through random walks. Then I will talk about how these objects are like sparsifications of some dense objects, sparsifications of some golden standard dense object, like for graphs, an expander graph is an approximation of the complete graph. So these guys will be some kind of approximation of the complete hypergraph. In general, high-dimensional expanders, we think of them as trying to generalize what it means for a graph to be an expander when you talk about hypergraphs. So a hypergraph is just a collection of subsets, but we will talk about something called a simplicial complex. Let me just first say what the outline for the talk will. So we will do the definition, talk about how it relates to the complete object, and then we will do another definition, which is through links. So this is a global definition, and this is a local definition, and we will show how these 2 definitions are equivalent. This is my goal. And then I will talk about applications. So there are 3 main domains of applications that I know about so far. One is the application for Markov chains, which I think throughout the past months we've seen some talks on this. So I will discuss this application a bit at length today, because after we do all of this, it will be very easy to prove the application. So I want to do that. And then applications to PCPs and a certain kind of testing called agreement testing, I will discuss probably in 2 weeks. And there's also applications to error correcting codes, probably also next time I talk. So today it will basically be applications to Markov chains. Okay, so I want to start by describing what is a high-dimensional expander through the definition of random walks. Okay, so in this picture, I have an example, sorry, of a high-dimensional graph. So it's just a graph, as you see, but in this graph we also have triangles. So I'm thinking of also this triangle as being present, this triangle as being present, and also this triangle. So what it really is just, if I draw it again, you should think of it as if we had a hypergraph with 3 hyperedges in this example. So I had 6 vertices and 3 hyperedges. But somehow it would be more convenient not to think of it just as a hypergraph, but also to do a downwards closing, so that whenever you have a hyperedge, which is just a set of vertices, you also add all of its subsets. So in this case, you also add the subset containing these 2 elements, and you draw this by drawing this edge, and you add. It is, I'm sorry, yes. Oh, but up to isomorphism, you know. Okay. So should I make it a bit clearer? You're right. Like this, and it's like this. Okay. So we add all we do a downward closing, and then this object becomes what people call a simplicial complex. So combinatorially speaking, a simplicial complex is just a hypergraph, except that whenever you have a hyperedge, you also have all the hyperedges of all subsets below it. And often when people talk about simplicial complexes, they have some topological setting in mind, and all kinds of topological knowledge is needed to understand what will go on. But in my talk today, I won't talk at all about topology. So the only reason I say simplicial complex is because I always want to assume that whenever I have a subset, I have all of the subsets below it.
It's a monotone function.
It's a monotone function. Yeah. OK. So here is, let's go back to my simplicial complex and think about what kind of random walks I can naturally do on it. So if I have a graph, so I ignore the triangles for a minute, then the random walk we always look at is the random walk that starts at a vertex, goes to some random neighbor, and lands at the vertex, and then keeps going. Go to a random neighbor and continue. And the way I want to think about it is you start from a vertex, you look at all the edges containing that vertex, you choose one of those edges, and then you go to the other vertex. So it's like going from a vertex to an edge to a vertex. Okay, so similarly, since we also have triangles here, we can do a random walk on the edges. We can start from an edge, choose one of the triangles that contains it. So maybe we should try with this edge. Choose one of the triangles that contain it, go to them, and then choose one of the edges in that triangle. So we move, for example, from this edge to this edge. Okay? And you can see this. Maybe I switch now. You can see this description of this random walk in this multi-layered graph, which is a less compact description of the same object. Okay, so what is this multi-layered graph? I put here all the vertices. So I have A, B, C, D, E, F vertices. Then I put all the edges. And then I put all the triangles. And if I had more dimensions in my simplicial complex, I would just have more and more layers. Okay? And it's also convenient to put the empty set down here. And now, what are these connecting edges? They're just edges for inclusion. So the edge df in this simplicial complex contains the vertex f, and it contains the vertex d. So you see that in this layer, every node has exactly two edges going out of it, because it's an edge, so it only contains two guys. Okay? And this triangle has exactly three edges coming out of it. But when you look at the number of outgoing edges on this direction, it doesn't have to be two. It can be a million, right? Because a vertex can participate in a million different edges. Okay, so this vertex participates in 4. The vertex D, you see that it has degree 4. Okay, so the random walk that we are used to on graphs starts from a vertex, goes to one of the edges containing it. If we start from F, we go to either EF or DF. And that you can see it on the picture there. You start from the vertex F. You can either go to this edge or that edge. And then once you're here, you can choose either to, now you're at the edge EF, you can go back to F or you can go to E. Okay, so you do one of these with probability half. So what you get is that whenever you start from a vertex, you go up to an edge, there's always probability 1/2, you go back to where you started. Probability 1/2, you go to a neighbor. So the random walk that you can look at by looking at a 2-step walk in this bipartite graph, what does it correspond to? It corresponds to the lazy random walk. Probability 1/2, you stay in place. Probability 1/2, you go to a vertex. So you see how the natural random walk that we're used to can be viewed in this layer. So we can also look at the random walk moving from edges to triangles and back. So here I'm thinking of starting from some edge, say DE, choosing one of the triangles that contain it. In this example, there's only one. And then choosing one of the 3 edges inside the triangle DEF. So maybe I go to this guy. Now you see, if you look just at this layer, you see that this bipartite graph is disconnected. If you start from one of the edges on the tail of this fish, you'll never move to the body of the fish, right? But that also corresponds to when you think of the random walk, when you think about that simplicial complex. You start from some edge, say BC. You can move to CD. From there, you can move to BD, to BC, to AB, but you will never move to that part. there is some disconnectivity. So even though as a graph it is connected, in one layer above, in one dimension above, there is something that is not connected. Okay, and we see it in this bipartite graph. Okay, so in general, what kind of random walks do we have? So we said we have the random walk that goes from vertex to edge to vertex. We can also go from edge to triangle to edge. And we can also go the other way around. So we can go from edge to another edge through a vertex. Edge to vertex to edge. So if you think of this drawing, this is just a cartoon, right? You can think we have many layers. So if you're at the layer of the edges, there's two natural random walks that we can do. One from edge to triangle to edge, and the other from edge to vertex to edge. Okay, so these are two natural walks. One is going up and then down, one is going down and then up. Okay, so notice that the down-up walk here is connected. If you start from the edge EF, you move through the vertex E to ED, and then through the vertex D to DC. So you can actually move throughout the entire graph. So this walk is connected, whereas we already saw that this walk is not connected. Okay, so these are not the same. Okay, and of course, so for the edges here, I have two different walks. I have it for every layer except the extremes, except here I don't have many layers in between. So for the triangles, there's no sense of going up. There's only a sense of going down. We add this empty set so that we can also discuss the random walks on the vertex layer, both going up and going down. So the empty set is connected to all of these vertices. And then the random walk, the up random walk goes from F to DF to D. And the down up random walk goes from F to the empty set to any other guy. Okay, so now we come to defining expansion. So let's first look at expansion. The random walk definition. But first, let's look at the case of graphs. Okay, so one very natural definition for expansion is to say that the random walk on the graph mixes. Okay, and the way we sometimes, well, there are many different definitions, but the one that I want to talk about is if you take the random walk matrix of the graph. So this is the random walk matrix of the graph. And you compare it to the all ones matrix, but maybe I multiply by 1 over n. So this is, I claim, a natural definition for expansion of graph. I say that a graph G is a gamma expander if the random walk is approximately the random walk which hops from vertex to vertex independently. Okay, so what is this? What is this object? This is the all ones matrix, but I normalize by 1 over n if n is the number of vertices. So it means that on every row in this matrix, I just have 1 over n everywhere. And it means that if I'm at a vertex v, the probability to go to some vertex u is uniform. So it's not really a random walk. It's just, when you look at the path in this random walk, it's just independent vertices. When you look at the path in this random walk, it's a path in your graph. And a graph is a very good expander if these two things are very close to each other.
So what's the norm?
Yeah, so what's the norm? So this is the spectral norm. So this is defined to be the norm of a matrix. Let's not use A, let's use M. It's just the supernorm, let's say, of MF divided by F for all F not 0. So this is like the 2 norm. Okay, this is not the regular 2 norm. And this is actually equal. So what are the eigenvalues of this matrix? So there's the all ones vector, it has eigenvalue 1. And all the other vectors have eigenvalue 0. Okay, so the eigenvalue, of course, okay, let me say something already now. To give the definition and to kind of work through the proofs, it will be very, very simplifying for me to assume that all the graphs and the complexes are regular. So let's make this assumption for now, and later on I can say what happens when it's not regular. So here, this is a case where it's not regular, because you see that this vertex has out degree 2 and this vertex has out degree 4. But let's for now assume that every vertex participates in the same number of edges and that every edge participates in the same number of triangles and so on. So allow me this assumption for now. We don't really need it, but it just makes life easier for me. So then the all ones vector that is an eigenvalue vector with eigenvalue 1 here is also the same here. So of course on that one they are identical. And then the fact that this norm is bounded by gamma just means that all the other eigenvalues are smaller than gamma, because this is 0 for any other vector, and this must be less than gamma. Okay? So this is just the definition that we are used to of spectral expansion. So this is just equivalent, absolutely equivalent to lambda n and lambda 2 being less than gamma. If you, yeah, for all, it's equivalent to all lambda I being, except for I bigger than 1, being less than gamma. It's the same. Okay, so I just wrote it in this way because I like this definition because it shows what it means to be an expander by saying something about approximation. An expander is an approximation for the complete graph. And why do we like expanders? Because they're sparse, so it's useful for us. Okay. So now we want to look at this definition in this multi-layered picture. Okay, and the way we want to, I want to look at it is to say, what is this this J? It's moving from a vertex down to the empty set and back up. The adjacency matrix for this random walk is exactly the matrix of all ones, right? Because once I moved here, I don't know where I came from, and everything is equally likely. Okay, so this random walk is described by this J, normalized. And this random walk, I want to say that it's described by this A. That's not correct. Because in this random walk, I have probability 1/2 of returning back to where I started, and only probability 1/2 to go to a new place, right? So the correct thing to say is that, okay, so I need to adjust for that. Okay, so now I will do that slowly.
Is it just adding a half J to A, right?
Half identity to A.
Yeah, half identity.
Yes. Okay. So now I want to define the up and down random walk operators. Okay, so basically we defined, maybe I just said it in words, but we defined what is the up operator. It's just the operator that moves me from one layer to the layer above it. So if I'm at a vertex, I take a random edge containing it, and I reached this layer. So I can view it as a linear operator that describes this bipartite graph. Right? So for every bipartite graph, I have a rectangular matrix that describes the adjacency, and it's a linear operator, so I go from here to here. Okay, so that's the up operator. Okay, it takes any function on the vertices and moves it to a function on the edges. How is this new function defined? At a specific edge, you average the function at its neighbors. So we're used to it all the time. We do it. So the up operator is really just this part of this bipartite graph, and the down is this part. So it's actually the same matrix. You just need to transpose it. And if I want it to be a random walk operator, you also need to renormalize. So For example, let's look at the edge versus vertices. Okay, so maybe here I have all the vertices, and here I have all the edges, and I put a 1 if in this location EV is 1, if and only if V is an element inside E. Okay, so this adjacency matrix, I can also write it this way, E and V. It's the same matrix. But if I want to view it as a random walk matrix, I need the row sums to be 1. So here I will normalize by 1/2, and here I will normalize by the degree. So up to a scalar, it's the up and down. This is the up operator, and this is the down operator. I take a vector, which is a function on the vertices. I multiply by this matrix. I get a vector, which is a function on the edges. So I moved up from vertices to edges. To go down, I take a vector that's a function on the edges. I multiply by this matrix. I get a vector that's a function of the vertices. So I went down. Okay, but these two, as I said, they're adjoint. Okay, so we defined the up and down. And now, of course, so let me denote this matrix by U and this matrix by D. So I can look at this. This now is a matrix, right? What are the dimensions of this matrix? V cross V. So this is a walk on the vertices. It's a walk that goes from a vertex to a random edge that contains it, and then from this edge to a random vertex that's contained in it. So that's exactly described by this matrix. And there's another matrix where you first go down and then you go up. And this matrix, what is this? What are the dimensions here? So these are E cross E. So this is a walk on the edges. Now this is a bit, right? So you go from an edge down to a vertex that's contained in it, and then back up to another edge containing this vertex. So that's UD and that's DU. Question? No. Okay, so now, of course, really I should have indices here, because these operators, if you imagine a very many levels, these operators can be defined anywhere. So really, you can write an index here to say that this operator works on level I. So it moves from I to I plus 1 back to I. And here I would, so again, if I write here, so the vertices are considered 0. So somehow the dimensions go like this. This is -1, this is 0, this is 1, this is 2, and so on. Somehow in dimension I, you have I plus 1 elements in your set. And this is because, you know, edges are like lines, so they're one-dimensional. Vertices are like points, they're zero-dimensional. Anyway, so in this example, DU works on level 0 and UD works on level 1. Okay. Okay, so now I can, I'm starting to get to that. So first I wanted to say, instead of A, I just want to write DU. So you go up to an edge and down to an edge. And instead of J, I want to write DU. You go down to the empty set and up to the vertex. So this is indeed true. It's true that J equals, so UD. You read it in English UD, but this is really first D is operating, so you're first going down, and then U is operating, so then you're going up. So this is the down-up operator. This is on level 0, this is equal to J with 1 over n. Okay, this is clear, right? Okay, so what about DU? The up-down operator at level 0. So this one is equal, like Avi said, it's with probability half, you're the identity. Because if you go up to an edge, then you have probability half of going back to where you started. And with probability half, you go to the random walk matrix of G. I didn't set up a notation for this, so let's write it this way. This is just the random walk matrix of the graph. Okay, so in general, I want to denote this part, the non-lazy part of the up-down operator. So notice that also if I go up-down in higher levels, there's some non-trivial probability of going back. So if I go up from an edge to a triangle, so a triangle contains 3 edges, so there's probability 1/3 of going back. So even if I'm at level 16, there's going to be probability 1/16 of going back. It's not negligible. So I always need to decompose this up-down operator to the probability of going back plus the probability of going to a new place. So the operator that goes to a new place, let's get a name for it. So we define Li plus the non-lazy upper random walk. Yeah.
Was the original walk already lazy? That's why you don't want that?
Yeah, this is the reason this was already lazy, because it was the composition of 2 operators. One goes up and the other goes down. So it doesn't. Once you are up, you don't remember where you came from. So you're up and down, and you may have returned to where you started. So, I mean, what was the original? If originally you think about this, then it's non-lazy. But if I want to generalize, I like this decomposition, but I also like to consider the non-lazy. So I need to define 2 different things for this. So, okay, so
does the Li include that kind of count of option? I mean, is that built into the Li notation? The 2/3 or the 15/16ths or the something, is that built in, or do you have to keep adding it?
So let's define it. I'm not sure. I guess I should say yes, it's built in, but to be sure, let me just say. So you start from some vertex. Start at S at level I. So by the way, if I have a simplicial complex X, then X with parenthesis I just denotes the sets of cardinality I plus 1, the level I in this complex. So you start at S plus Si, and then you choose uniformly some t that contains S and t is in xi plus 1. So you have many options. You choose each of them at the same probability. By the way, once we have weights, this will not be uniformly anymore. We'll have to take the weights into consideration. But for now, I'm just imagining that all these bipartite graphs are biregular, and then you're starting at level I. You choose one of your neighbors at random, so you go here. And then the second step is choose some S prime contained in T such that, so 2 conditions. If I were just going down, I would just say S prime has size I, and that's it. I mean, belongs to layer I, and that's it. But now I also need to say S is not equal to, S prime is not equal to S, and S prime is in Xi. Okay, so I described some random process, and Li plus is just the matrix of this random walk.
But S prime will always be in Xi.
Say again?
S prime will always be in Xi.
Yeah, I mean, contained in T, it might be lower. I mean, when you just say this,
Oh, I see.
so I just need to say that it's in Xi. But another way to say it is choose an element of S to knock off, yes, of T to knock off. Okay, so this is the non-lazy upper random walk. And the observation that we are now making is that Li plus, so I'm leaving some space for some scalars here, equals the up-down random walk. Right, so if I'm going up and then down, and I'm at level I, okay, then I'm going up to a set of level I plus 1, so it has size I plus 2. So with probability 1 over I plus 2, I will stay in place, and with the remaining probability I plus 1 over I plus 2, I will do this. So I have this equality. Yeah.
Wouldn't it be exactly the same to say you choose uniformly S from the same level that has how many
Great question. Choosing
Because for them,
S.
there's exactly one common element on size I+1 that contains both.
So the thing is, if you have S and another S prime, and this is I+2, and these are the two different things. The difference, so this step from this guy to this guy is always allowed when you go down and then up, but it might not be the case that this collection of I+2 elements are inside your complex. So when you go this way, this step might not be allowed.
Okay, so this would be the down walk.
So the down non-lazy would be what you said.
So, but the up you need to
The up you need to see what's above. So I think if you really need to be, if you really want to be a saint, you should also consider the down-up walk, the non-lazy part of this and the non-lazy part of this, and compare them. But somehow this is always, this is never helpful. So, how to say? Being a saint is not a good idea. Somehow, okay, so what to say? It's just that the laziness component in this walk is so small that removing it, we can ignore that. Okay, and somehow in the examples that I know, computing it is complicated, so I don't know if it's helpful. Okay, so far we defined the up and the down operator, and we defined the non-lazy, which is important. Okay, good. So now going back to the definition of expansion for graphs, what I want to say is L plus at level 0 is exactly the random walk matrix, because it's the non-lazy thing. From a vertex, you go to a random neighbor. You don't stay with probability 1/2. So A is, this capital A is, I could replace it by writing L0 plus. Okay, and so the standard definition of expansion just says that L0 approximates what? Approximates the down up. So really, I've come to this thing that the definition of expansion says that there are two random walks on the vertex level. One of them is the L plus, and one of them is the down up, and they are the same up to some gamma. So this is the definition. So the definition, so I write it again. So the definition is that L plus at level 0 minus the down up operator also at level 0 is less than gamma. This is, we've seen this is equivalent to the graph. The graph is a gamma spectral expander as per the normal definition of eigenvalues. So this is, so far it's okay? Okay. So now we will generalize it by just saying for higher dimensions, you just do it for every I. So the definition, X is a d-dimensional simplicial complex. So let me just write complex. X is called a gamma, let me also add the word two-sided, a random walk HDX, high dimensional expander, if for every I up to d minus 1, I guess, we have that Li plus minus du that works on the same level is less than gamma. Okay, so we look at this multi-layered description of the complex, and we want that at every layer, this walk and this walk are roughly the same up to this gamma error. Okay, so this is our definition. There's also a one-sided definition, so let me just also say that. Oh, thank you. I want to. Why not? Yeah. So that's not the same. So in algebra or in topology, there are boundary and co-boundary maps which also do the same kind of thing, but there they have signs. So so there's two variants that are kind of important in this area. One is when we are looking at these operators as linear algebra operators, I told you, oh, if I have a function on the vertices, I can move to get a function on the edges. So when I said function on the vertices, what was this function? What was the range of this function? It was to the reals. So I labeled every vertex by a real number, and then I did this operator, and I got a real number for every edge. I can also label it by any other abelian group, for example, or in particular with the binary field with two elements, F2. And I can do this thing. So now every edge will XOR the two. And then what we will get is exactly the co-boundary operator if we move up, and the boundary operator if we move down. That's true. But this just happens to be the same because for F2, minus and plus are the same. For any other abelian group that doesn't have characteristic 2, these two operators are different because the boundary operators have some sign issue, and we're not doing any signs.
So then in F2, you don't have one over D.
Yeah, none of this will work in F2. You need to think about different things, and this is not for this talk, maybe some other talk. These are really super interesting things, but today I'm going to just talk about these kind of random walk and mixing properties. Okay, so we made this definition. So let me tell you before we continue that why would this be a good definition? So for graphs, it's natural to have some golden target object that's like the golden standard, like J, or the complete graph, which is your target object. And then your expander is a good approximation of this dense object. So now I want to claim that this definition is good because a complex that satisfies this definition is a good approximation of the gold standard for hypergraphs. So what is the gold standard for hypergraphs? It's the complete hypergraph. So I want to say that these things are a good approximation of the complete hypergraph, and we'll do it slowly. I'm just realizing this. Thank you. Yeah. So let's do the one-sided, and then we move to the gold standard. So we said that X is a d-dimensional complex. It's a two-sided random walk if you have this bound. And the meaning of this bound with this norm thing is that the operator written inside here, it doesn't matter what it is, all the eigenvalues in absolute value are bounded away by gamma. The one-sided will just say that lambda, maybe I used the blue, lambda of this operator, Li plus minus UD, can you see the blue? Okay, is less than the same gamma. And what do I mean by this? So let's just define it here. It's lambda of an operator M will be the supremum over because I want to allow signs, so I'm not going to do norm, I'm going to do MF inner product with F for all F that are okay, so I guess I will just say normalized. Okay, like this. I mean, sometimes we also add F orthogonal to 1, so it depends. Let me define it like this: F orthogonal to the all ones. Okay. In this definition, I don't need it because the all ones will cancel out anyway. The all ones vectored on this particular M has eigenvalue 0. So I don't need it there. But in general, let me make this definition. So for example, for a bipartite graph M, it has an eigenvalue that's -1. Okay, but -1 certainly doesn't maximize this supremum, so it will be allowed. Whereas in this definition, eigenvalue of -1 won't be allowed because you can't bound it by gamma. Okay. So this is a definition for high-dimensional expanders. For every layer I, this is an...
I mean, what would be an analog of a complete bipartite graph in the case of two-sided versus one-sided high-dimensional expanders? Would it be like complete multipartite?
Yeah, it will be the complete multipartite graph, but some very nice theorems that we know how to prove for the two-sided cases. Like in the two-sided case, I can say this complex approximates the complete hypergraph. In the one-sided case, I don't know how to say it. Maybe it's true, but somehow so.
Where did this one-sided come up? What is this guarantee?
The definition just, please.
In a bipartite graph, you can have the rapid mixing. It can be a very good random walk will convert fast, despite the fact that some eigenvalue is an absolute value 1 and it's -1. So you want to capture, if you want to capture expansion or mixing as opposed to spectral bound, then you can allow just one-sided definition and you still get mixing.
I'm sorry, because I cannot read there. What is under the soup?
Just normalizing f and having it orthogonal to the all ones. It's what you would naturally, usually we define like the maximum between lambda 2 and absolute value of lambda n. So, yeah. But here, in this definition, it's just lambda 2, actually. This is just, I can even add a 2 here. Because you're just saying lambda 2 needs to be bounded. I don't care about lambda n.
Do you need the down degree to be the same as the up degree for all ones to be in the kernel of that?
There's a way to make this definition work no matter what the regularity is. And yeah, for now I'm not getting into it. It's really a technicality, like there's nothing deep going on. Okay. So now I want to get to this so kind of a natural goal is to say h dx is like approximating the complete complex. And let me denote it by delta. I guess I don't know where to put the different letters. So it's n vertices and the dimension is k. Okay, so it's just like the Johnson scheme. You have a ground set of n elements, and you have all possible k plus 1 subsets and downwards closed. So that's what we call the complete complex. Now, if you think about it, and okay, you didn't see all this stuff, and you would, from elementary considerations, try to think how would you define something that approximates this in terms of random walks. Then, okay, at the level of vertices, we actually have already, this has been done for us, and we have this definition that J is the complete complex at level 1 or 0, and A needs to approximate it. But now when you move one level above, you're talking about random walks from edge to edge in two different settings, in the setting of this delta and in the setting of your complex X. Now, how many edges does this delta have? It has n choose 2 edges. So the matrix describing this random walk is n choose 2 by n choose 2. Now, if you look at your complex X, you want it to be sparse, so maybe the number of edges is less than n choose 2. So you have a matrix of size E by E, and you want it to approximate a matrix of size n squared by n squared. So how will you define it? So I don't know how to do it that way. Instead, this way kind of gets around it because you're not comparing random walk of X to delta, you're comparing a random walk of X to another random walk of X. And the sizes of the matrix are the same. But still, I claim that we got something that allows us to compare these two things. And this is the lemma I want to say, is that the lambda 2, so okay, let me write it formally. So if X is a k-dimensional gamma h dx, and here I'm not writing one-sided or two-sided, this is actually true for both, then lambda of x equals lambda, sorry, not lambda of x. So now for every I, then for every I less than k. So now I'm going to think of all these random walks on all the levels. And I'm going to look at lambda of L plus. No, where did I write the plus and where did I write the I? Okay. Okay. This lambda of L plus I equals lambda of x. Of x. Okay, so I can either write equals lambda of L plus I of delta. Okay, let me write it. Equals lambda of L plus I of this delta guy plus, O of gamma. So I'm saying that the lambda of these two random walks are the same up to some error of gamma. It's measuring how close you are. And this is good, right? It's like measuring something that we wanted. I can also just give the formula. So lambda of Li plus equals, what is the best, what is this lambda in the case of the complete complex? So let's say compute it for a minute. I'm at a set of size I. Okay. I need to do this computation. Okay, so let's leave this blank for now. I want to do some calculation, and then I will write here the number.
What did you have here? Plus lambda of Li plus of delta plus what? O of L?
O of gamma. So this is the error term. So, big O. So plus big O of gamma. So basically, I'm saying this is our golden standard, the complete complex, and this is my expander, and I'm saying the spectral gap is the same up to error gamma, and gamma is the parameter of the HDX. Okay, so I want to prove this. We will prove it inductively, and we will start by and we will do it by actually proving the right number here. Okay, but to know what the right number is, let's do a calculation first.
The right number you're looking for is the right number for the complete complex.
Yes. So you can ask yourself while I'm erasing, what is the right number for the complete complex, and how would I calculate it? So you know that to understand like the eigenvalues and eigenvectors of a very combinatorial kind of graph, it makes sense to look at subsets of the nodes that are not very expanding, and this will give us a good idea about who are the eigenvectors that have the lower eigenvalues. So who are the non-expanding sets, or the not very expanding sets in delta? Okay, let me tell you. Suppose I'm at level k. So I'm now going to define the set 1 v0. I'm going to define now a function called 1 v0. Its inputs are S is a subset of the level k, so it has k plus 1 elements. And this function is just defined to be 1 if v0 is in S, and 0 if v0 is not in S. Okay.
The intuition is that sets contain, a family of sets contained in one bigger set are not very expanding.
Family of sets that contain, it's like a star.
Sets that are not very expanding, you can take a subset and take all its subsets.
Yeah, but actually here it's the dual. It's all subsets that contain a point. Those ones are good when k is very close to n. These are good when k is like very small compared to n, which is what I'm thinking about right now. Okay, so let's see. You know what? Let's fix k yeah, what should I fix k to be, like 3 or something? Okay, so let's fix k to be 3. So, or no, let's fix k to be 2, and S has size 3. Okay, so now I want to understand what does L plus at level 2. So you're moving from a set of size 3 to another set of size 3. In the complete complex, it doesn't matter if you're how you're moving. It's all the same. Of S. What does it look like? Right. So you started with a set that contains V0. You go up to 4. So you're always allowed to go up to 4. And now you're removing one of the vertices. So you have 4 vertices. There is some probability that you will remove V0, right? But it's only 3/4, so there's still a good probability that you will stay inside your set. So it's roughly 3/4 if V0 was in S, and it's roughly 0 if V0 was not in S. If V0 was not in S and you moved up, you got a 4-element set. What's the probability that V0 is here? It's almost 0. It's like 1/n. And now the probability you remove one of the vertices, you're not in it. So that's why here it's almost 0 and here it's 3/4. So you see that this function looks almost like this function. I mean, I cheated here because there are some extra probabilities, okay? But this is roughly an eigenvector of L plus. Do you see what I mean? I'm saying that, so this is roughly, I'm saying that this is roughly equal 3/4 times times the original guy, 1S. Okay, now sorry, 1V0. So the point is that this operator A plus, you gave it some function, and you got back a scalar multiple of this function. Now, you didn't get it exactly, and you shouldn't have expected it, because this function wasn't even orthogonal to the all ones, right? So it cannot be an eigenfunction. So you need to change it a little bit. Basically, if you remove the all ones from it, then it will be okay. Okay? Then it will be a complete, a perfect eigenvector. Okay, so you see that the eigenvalue here is 3/4, and in general, I want to write.
These are the worst. These are the largest.
So this is what I claim, and now we will prove it. So now just help me. So 3/4 is, I guess, I plus 1 over I plus 2, is it? Is this correct? I had 2, and I had 3/4. This is correct, right? Okay.
There's also some confusion between.
No, it should be.
The three-dimensional is having size k plus 1, right?
Right, but if I have 0 here, I want this to be. I want this to be a half, so it's fine. So it's okay. All right. So this is the lemma.
Okay, so the first term is really the eigenvalue of the full of the complete complex. I plus 1 over I plus 2 is maximum.
All right, so yeah, so what you're saying is let's check this lemma for the case I equals 0 in the complete complex. And so you get here 1/2, and we know that in the complete complex, what is this L plus? It's you move from a vertex to a random edge containing the vertex, and then to one of the two guys. So with probability half, you should stay in place, and then with there, that's it, and you don't have even this extra term. So this is true for the complete complex. And now I want to inductively get it all the way. Okay. So I guess I will do this, and then we will take a break. And then we do the links after the break. I have some other board there, or no? I guess not. So there's actually 3 things that I need in order to prove this. So let's write the 3 things. The first is the definition. So I need I need my definition that lambda of Li plus minus ud is smaller than gamma. This is the definition. Okay, I'm going to do an inductive proof. So for 0, we already saw it. And for bigger i's, now we'll do an induction. So I need this. This we know by definition. I also want the fact that lambda of any u transposed is equal to lambda of u transposed u. This is true always, just because if v is an eigenvector for this guy, then I guess u transposed v is an eigenvector for this guy. So this is always true for any bipartite matrix. And in our case, instead of u transposed, I'm just going to write the down operator. So this is, let's say, a standard fact about a transposed, I don't know. Just that the spectral gap going this way is the same as the spectral gap going this way. Now notice that this operator works on the level of I minus 1, and this operator works on the level of I. So here you go down from I to I minus 1 and back up. And here you go from I minus 1 to I and back up. So you're talking in both cases about the same bipartite graph. One operator goes from here to here and then here. That's one of them. And the other goes from here to here and then back. So there are these operators are working on two different spaces, but they're described by the same two matrices. And that's why this is true. And what is the third fact? The third fact is just this formula. Okay, let's write it again. That the up-down operator is equal to, on level I, is equal to 1 over I plus 2 times the identity plus I plus 1 over I plus 2 times L plus I. Okay, so this we already saw. Okay, so now that we have these three things, I have it here. Okay. So I want to compute lambda of Li plus, and I know by the first bullet that it's less than lambda of ud plus gamma, plus O of gamma. So from the definition of lambda, this is linear. It's okay to translate that to this. Okay, so now what is lambda of ud? This is ud at level I, yes? So this is the same as lambda of du, but now du, so ud at level I, from I to I minus 1 and back to I. So now this is du at level I minus 1 plus O of gamma. Okay, now I'm using the second line. And finally, du, I can write it as L plus, but now since I'm at level I minus 1, I plug here I minus 1, and I'm going to use the induction. So what do I get? So I need to not make a mistake. So I'm plugging I minus 1, so I get I plus 1 plus I divided by I plus 1 times whatever I deserve to get by induction. So I copy it from the claim, I divided by I plus 1. I divided by I plus 1 plus, so I have here plus O of gamma, and also, well, I guess here I didn't need the O, I just had gamma. So plus gamma, so that's fine.
When you go from UD to DU, you lose the level.
Yeah, that's how I do the induction. I move one down. So you can bookkeep this, and you can even do it better in some, but I'm not doing it. So for me, this is just O of gamma. Imagine it's only a constant number of steps. Really, you can see that you're only gaining a gamma at every step. So what did I get here? So forget about this. No, something should have canceled. Not really. So
The second step is an equality, right?
the second step is an equality. No, but I have a mistake here. So,
You're going up on the induction. It's I from the bottom.
it's from the bottom, right? So
Maybe you
I,
want it down, up, and then up, down.
no, Li plus is really like the up down, and then the up down is like the going down and then up is like going up and then down, but from level I minus 1, so that's fine. And then this one I express as a combination of two things. So I guess it's
Maybe it was I. Maybe it was one over I or something.
You get the expression of I minus 1, right?
yeah, Li minus 1, so I need to write here I by I plus 1, right?
Yeah, but the formula for Li, was it correct or what?
This formula?
No, the formula in a box upstairs.
Ah, this one?
Yeah, it's not.
Is it
the
correct?
Maybe it's I over I plus 1.
For I equals 0.
For I equals 0. So with probability half, you do this. And with probability half, you do the identity. So, okay, maybe take a break and I'll figure it out and then we continue.
So maybe I just want to say something because Irit didn't say. So, I mean, you are getting the final, beautiful, correct definition of high-dimensional expanders, but it took a long time. High-dimensional expanders exist for maybe 15 years or more than 10 years. Lubotsky and Samuels and Vishna defined it, and it was defined by some family of Laplacians of this complex, and then other people defined, Linal and Roy, what's his last name? Roy
Meshulam and Linal. Yeah, I will say it at the end.
And then Lubotsky and I don't know, Tariq Kaufman defined it somehow like with property testing, and before that Gromov defined it using various topological, some topological definitions. The relations of all these, definitions of expanders were not clear, and some of them got clarified. And then I guess maybe Irit and Tali that got this random walk definitions, and the whole field simplified, at least for me.
Okay, we will talk about this more in the second hour.
If the graph isn't regular, what do we need to adapt?
You do what you do for normal when you want to get a Laplacian, right? You multiply by the diagonal of the square.
The way that I prefer is you define an inner product on your space that is weighted by the stationary distribution. So a vertex that has more edges has more weight. And then the up and down operators are adjoint according to that inner product, and everything just follows. So
It is the same.
it's the same.
What you do with square root of diagonal is the normalization.
Yeah.
You're doing a
Yeah, it's the same. Yeah, it's just okay. So okay. L plus is the guy that doesn't have laziness. So if we check it for 0, L plus of 0 shouldn't be 1/2 plus something. It should be 0. Okay, so L plus is the random walk. Okay, so it was I plus 1 over I plus 2. I changed it. It's I over I plus 1. When you plug in 0, you get your 0 divided by 1 plus O of gamma. So it works for 0. And now inductively, so this decomposition I didn't change. So it's just copying this but plugging in I minus 1. So you get here 1 over I plus 1 plus I over I plus 1 times the L plus of I minus 1. And I plug in the inductive hypothesis, and now I get this cancellation. So I have 1 over I plus 1 plus I minus 1 over I plus 1, which gives me I over I plus 1, plus the error term. So that's it. So that's the proof. Fine. I mean, it doesn't really matter what the proof is. The point is that it comes out of very simple considerations and inductively. And this is also the way to calculate so it's not only the way to prove that an HDX is close to the complete complex, it's also the way to calculate the eigenvalues for the complete complex. It's the same kind of inductive argument.
Does this mean that the first layer is always a general
Yes. It's also by definition, because we require for every layer, including the first layer, that the difference is a small gamma. So, but yes. So, so I want to comment. Oh, question?
The error term can be just gamma, right?
I think it's gamma times I. So you collect gamma at every iteration.
Gamma times.
And maybe there you can save a little bit, and I think there's some paper in the upcoming stock that does it, but for now this is good for me. So to conclude all of this, I want to say that this definition of high-dimensional expander tells you that high-dimensional expander is a pseudo-dense hypergraph. So this is like the densest hypergraph on dimension k, and X is pseudo-dense with respect to this. Well, it has the same spectral behavior as this dense object. Now, usually we don't say pseudo-dense, we say pseudo-random. Right? We say, oh, an expander is a pseudo-random graph. But that is true because it happens to be that this is the dense object, the complete graph. A random graph approximates it, and a random graph is an expander. Okay, so it's true that the graph is a pseudo-random object. But this object is not pseudo-random. No random hypergraph, no matter what edge density you choose, that's not correct. With small edge density, no random hypergraph with small edge density or hyper edge density will have this behavior. It will be completely disconnected. So only think even of dimension 2, so triangles, okay? If you have a complete one skeleton, so you have all the edges, plus you have roughly n squared log n triangles, then indeed this will behave like the complete complex. But if you have fewer triangles, say you have only n squared triangles, or no, n squared is not a good example. Maybe like linear triangles, linear in the number of vertices. So suppose you have n vertices, and you give there 1,000 n triangles. Okay, then think of a specific edge. Okay, how many triangles will be inside and on it? Okay, maybe 1,000, and you won't be able to move. So you start from a triangle, you move to this edge. That's your movement. That's it. So it won't be connected at all. But so how did this definition come up? Really, like someone from background like mine could not have come up with this definition, because usually you make a definition, you try some random graphs, you see the definition doesn't hold, so it doesn't exist. So you wouldn't make this definition in a million years. So the way it came up, so Avi was saying it before the break, is that people tried to define expanders in hypergraphs in many different ways, including Avi in a paper decades ago. And the different definitions are very different. So for graphs, they all coincide. But once you generalize different graph definitions, you get completely different things. And usually they're not very useful. For example, for graphs, you have an adjacency matrix, and you can do spectral decomposition. For hypergraphs, you have tensors, and tensors are very difficult to deal with. So these things are very difficult. And one thing that happened is that there was this beautiful, famous expander construction by LPS, Lubotsky, Phillips, and Sarnak. This is a beautiful construction of expander graphs that takes the infinite deregular tree and does some quotient, so it looks at it as if it's a Cayley graph, and then it uses some group to quotient it by identifying vertices that are in the same orbit of some group. You get a finite object that looks locally like the tree, and they prove that it has beautiful spectral behavior, and that's how they constructed in the late 80s their first Ramanujan graph. And what later happened is that some deep math goes into this, and the math developed, and people were able to construct higher dimensional analogs of this kind of quotient. Okay, so there's some analog to the infinite tree. It's called the infinite Protitz building. And there are groups that you can quotient, and you get a finite object that's the quotient of this thing. So Lubotsky, Samuels, and Vishne worked very, very hard to get this to work, and they constructed this object effectively. And they said, here, we have this object. This is a high-dimensional expander. Now, it's not like they had some definition of expander. They just knew what the object is, okay? And they constructed it. And now you can look at it and start to see what properties does it have. Okay, so it has a lot of beautiful properties and many different definitions that are not equivalent to this one. And in particular, it has this property, but this is not how it came about. Rather, people looked at the different definition, which is the definition through links. So now I want to talk about a different definition for high-dimensional expanders, which is the link definition. It's a local definition. And then I will prove that these two definitions coincide.
You said infinite something building. What was the something in the middle?
Bruhat-Titz building. Yeah. This Bruhat-Titz building is like to understand groups of matrices over the reals. You look at R to the n, and this is your playground to understand what the matrix are doing to vectors in R to the n. Now, if the matrices are not over the reals but over some other fields like the p-adics, then the Bruhat-Titz building is the replacement for R to the n, which is kind of the playground where your matrices are working. Acting, I should say. Question?
Yeah, I was just going to ask. So, I mean, we don't have random high-dimensional objects as an expander anymore. Is there any other simple example other than that comes from this?
Okay, so we have the complete complex. Sure. It's a wonderful example. And then there are these very complicated constructions. And there's a beautiful construction by Tali Kaufman and Ishal Oppenheim that it's still group theoretic, but somehow it's very elementary. And if you want to read it, there's a beautiful exposition by Harsha and Saptarishi. It's on the archive. Basically, they take the Heisenberg group and subgroups of it, and they take vertices for the cosets in this subgroup and connect two cosets if they intersect. And then you can analyze the properties of these things.
Yeah, but your question, you asked about spars.
Yeah.
Spars, these are the only constructions.
No, the Kaufman-Oppenheim as well.
No, but it comes from the same. It can be viewed as
It's some kind of.
this Bruhat-Titz building. And
Yes.
Nobody knows of another.
I mean, yeah, a major question is to get a zigzag. We have this zigzag construction for expanders. Can we get something like that? Yeah, that's a beautiful question. There have been several papers constructing high-dimensional expanders, but they're all weaker than this in some way that I can say after I give the link definition. So there are some combinatorial constructions, but to me they're not they don't cross some barrier that these guys do. So I'll talk about it. So now I want to do a definition of HDX, a link version. So what is the link of a face or a subset in a hypergraph? It's you look at, so let's start with the link of a vertex. So link of a vertex. So if you have a vertex V in this picture, in this fish picture, the link is to look at all the neighbors of this guy. Those are going to be my vertices in my link. And then look at all the triangles containing this guy and see the let's look at the link of C. So the neighbors of C are A, B, and D. Okay, so I'm looking at C. So I have A, B, and D. So the neighbors are A, B, and D, but I also put these edges because these come from the triangles that contain C. Right? There was the triangle ABC, and there was the triangle CBD. Okay, so now this is the link. It's a one-dimensional-less simplicial complex. In this case, it's just a graph. Okay, this is the link of C. Let's look at the link of D. So the neighbors of D are B and C, and F and E. And there are two triangles, so this is the link of D. Okay, it's a graph, but this guy is disconnected. Okay, it's disconnected, and this disconnectivity is exactly responsible for this disconnectivity here. So it's not a coincidence. Okay, we talked about the fact that this random walk is not the same as this random walk. This guy is connected and this isn't. And the link of D is the guy that's to blame. Okay, so if you want your random walk to mix, for starters, you will want all the links to be connected, and you will want them to even mix more than just be connected. Okay, so by the way, you can also have a link of we call it a face. The hyperedge in a simplicial complex is called the face of a face S. It's just the collection of all t minus S, where t contains S and is inside the complex. Okay, this is xt. So I just wrote xt as a collection of subsets. Of course, it contains both vertices and edges and so on of all dimensions up to t minus s. Question? X. Sorry. Thank you. XS. Okay, so that's the link. And you can see that if you have a high-dimensional complex, even in the case of a three-dimensional complex, so it's a complicated thing. And when you move to the link, you get just a graph. And graphs we already know how to analyze very nicely. So it's nice to look at the link because it gives you a way to look at a much simpler object. And what is it, the link? It's like you condition on S, and you look at the remaining probability. So we do that a lot when we analyze probabilities and so on. Yeah. It's like restricting. Okay, so what is the definition? It's just saying, let me write the definition here. So let X be a k-dimensional complex. X is a gamma link HDX. If for every S, for every face of dimension less than d minus 1. So notice k minus 1. Thank you. So if you're k-dimensional, if I look at, k faces have nothing above them. K minus 1 faces have k faces above them, but these are just disconnected. There is nothing connected. So the first place where it's interesting is to look at k minus 2 faces. So S is dimension k minus 2 or even below. So for every S of this dimension, dimension is the level, not the size. K-dimensional means size k plus 1. XS. Okay, if S is let me also say let GS be the graph. So I'm sorry the definition looks complicated. It's really easy, so we'll parse it again. The graph underlying X underlying. We also call this the one skeleton. It's the graph underlying XS. So notice that if the dimension is some k and S is some, I don't know, k over 2, then this complex itself is not a graph. It's some k over 2 dimensional thing. But I can just look at the vertices and the edges of this guy. So then I call this GS. It's a graph. The definition says that the lambda of GS needs to be at most gamma. So the definition just says for every S, the local spectral gap is big. For every S, lambda of GS is gamma. This is what the definition says. So you can make a two-sided or a one-sided. You can also write, that lambda 2 of GS is at most gamma. So I guess here I will use lambda to denote the maximum between lambda n in absolute value and lambda 2. And lambda 2 is just lambda 2.
Do you want dimension of S be exactly k minus 2?
No, for all, for everyone.
Because if S size 2, then what is the graph exactly? If S is smaller than k minus 2, it wouldn't be a graph.
Right. For if F is smaller than smaller, then what you have is a complex. It's not a graph. But then you look at the graph underlying. It's a complex, so it has triangles and edges and vertices. Forget about the triangles. And what you have, you look at this spectral gap. Okay? And now, I just want to remark, because people ask me about the case of weights and non-regular. So also here, it's not just that you look at the graph and that's it. You also inherit the weights on the edges. So you should always have, what you have is a probability distribution where you start with some probability distribution on your top faces, and then you think of this kind of random walk that you choose some guy at the top, and then you move to one of its children uniformly. So this movement is uniform, but what you will get here will not be uniform, because if an edge participates in many triangles, it will have bigger weight. Okay, and when you look at the links, you should inherit the weight. But all this is not important for this talk, because I'm doing everything regular, so pretending that everything is regular. Yes, thanks. Okay, so no, it's good. So basically, forget about this sentence. I should have defined it outside of the definition. So let GS be the graph underlying XS. So this is per Andre's comment that the link is not always a graph. In the example that I drew here, the links were graphs, okay, because I only had a two-dimensional object. But if I had also higher dimensions here, then if I look at all the sets containing a vertex, I would also have triangles and stuff over here. So I'm saying, okay, look at this complex, ignore everything above the edges. So just look at the vertices and the edges and call this G sub S. So I have here for every S, lambda of G sub S is bounded. So basically there's a spectral gap at the link. Now, maybe I should also emphasize, what is lambda? This is a graph. What is lambda of this graph? I mean lambda of the random walk matrix. Or really what I mean is that this lambda should be normalized. So for this to have meaning, I always want to talk about the random walk matrix of whatever graph it is, so that the eigenvalues are always between -1 and 1. And then it makes sense to say that lambda is bounded by, I don't know, 0.1 or something. And when I talked about these combinatorial constructions, some are really very nice constructions, they always have lambda 1/2 or bigger. And lambda 1/2 is some threshold for many local to global phenomena to occur. So, okay, we will.
L1 of X sub S.
L1?
Like this L sub I operator.
Yeah.
You write like L1 plus some X sub S or something like that.
Yeah, I guess I could. Yeah.
Because when you write it that way, it really looks like this definition is weaker than this definition.
So you're suggesting to write here lambda of L0 of GS. Yeah, it's L0 because you're walking on the vertices, yeah? Yeah.
No, but he also just wants you to write XS.
X sub S, right?
Oh, I see. I don't even need G sub S.
Yeah.
Ah, perfect. Okay, so I can erase this.
Yeah.
Awesome. It's just my height. Okay. Okay. Okay, yeah.
So, I mean, unless I'm missing some gigantic thing here, it seems like it doesn't really care about the higher dimensional. It just cares about the one skeleton.
No, that's not true.
Well,
No, thanks for the
I'm
questions.
sort of setting that up because, in fact, it would seem then that it might not care about anything other than the one skeleton, except for the fact it's a simplex, which kind of forces relationships between things that kind of give it some aspect of understanding the bigger picture.
No, but notice that here you are conditioning on S. So this whole thing, even if it's a graph of only those triangles that contain your vertex. So it's noticing very much. So for example, this X sub S has nothing to do with the entire skeleton. The entire skeleton can be, say, complete, and X sub S can be disconnected. You see, like in this example, this would be X sub S when S is the vertex D. This is the link of D. You see, it's disconnected, even though the one skeleton over here is connected. Does that make sense?
I mean, I would think that if, forget about the triangles, the faces in that, your example there.
Mm-hmm.
If I were looking at the neighbors, the link of D, I would come up with this. Oh, I see. The point is that the link actually has edges in it.
Yeah.
It's not just the vertices that are neighbors of it.
Yeah, that's the point. Yeah. Okay, any more questions?
So
Yeah,
why do
that's
you,
go on first.
so you stop at dimension k minus 2. So which level of that graph is that?
K minus 2. Over here?
Yeah.
It's just that, for example, in this example, K, it's two-dimensional. So I only take links of vertices.
Three-dimensional or two-dimensional?
It's two-dimensional. It's two-dimensional. So k is 2. And the vertices are zero-dimensional, so they're less than k minus 1. So it's exactly, you only look at links of vertices. Because look, if I look at a link of an edge, it's defined. The link of the edge BC consists of 2 vertices, A and D. And nothing, no edges. So it's always going to be the case. So it doesn't make sense to look at links above k minus 1.
So does it suffice to restrict the hypergraph to dimension of S plus 2 uniformity edges, and then the link graph is still the same?
Yeah. Okay, so now the claim I want to make is that X is a gamma random walk HDX, if and only if it's a, well, okay, I don't know about the gamma and the gamma prime. There is some maybe difference, okay? If it's a gamma link HDX. Okay, so that these two definitions are the same qualitatively. Okay, and so what's interesting is that the link definition is very local. You look, even in the two-dimensional case, it's already very interesting. So you look at every vertex and you require the neighborhood of this vertex, when you think of it as a graph, first of all, it needs to be connected, so this guy isn't. And secondly, it doesn't only need to be connected, it needs to have some spectral expansion. Now, maybe let me emphasize, you could have a two-dimensional complex that is pretty sparse. So it could be that the link of a vertex contains only a constant number of vertices and edges. Okay, this is actually the complexes that this algebra guy is constructed. It's sparse. So every vertex contains a constant number of things. Okay, and what does it mean to require for a constant size graph to have a bounded spectral gap? It still makes sense if you look at it as a random walk. Okay, if you normalize the eigenvalues, saying that they're close to 0 is very meaningful. And what I'm saying is that actually we don't have any combinatorial construction that achieves gamma smaller than 1/2. Anyway, going back to this theorem, I want to say that this is a very local definition. It talks about what's happening around every vertex separately. And this is a very global definition because it's talking about the entire random walk. But actually they're the same. So let me show you just the proof of this direction, which
So can I ask, I mean, even here you can split this both statements into levels.
yes,
Would you then have an if and only if at each level?
yes, yeah. We'll see from the proof. Okay, so let me prove this, and before I prove it, so I guess, is it really 11:05 or is it really 12:05? I was so optimistic. I was doing so well on time. Okay. Okay, so I see. So that's okay. I think we will make time. So the reason I'm proving this direction is because for the application to Markov chains, what happened is that it's very easy to analyze the links, and you can show very easily that the links are actually, in some cases of interest, like matroids, they're 0 HDXs. Okay? And this implies that you are a 0 random walk, a one-sided random walk HDX here, and this immediately implies mixing, finish. So kind of the way this theorem was discovered was through connections with some very, deep things in other area, Lorentzian, real stable polynomials. I don't know these things, but when you strip it down, it really boils down to some very simple combinatorial inductive arguments that, like the kind I'm showing you. Okay, so let's see the proof. So I want to show, suppose X is a gamma link HDX. Yeah.
So this gamma, when you write it, it's in absolute value or not in absolute value?
Okay, yeah, okay. So I'm trying to cheat a little bit, but this theorem, the if and only if, is only for the two-sided case. This direction from here to here is also for the one-sided case. Okay, so that's why okay, so the theorem is for the two-sided. So this is for the two-sided definition. But now the proof I will show is actually, for this direction, will prove something slightly stronger, which is for the one-sided. Okay.
Do you expect the one-sided if and only if is in fact true, or is there a counterexample that says it's not?
So I don't know. So I don't know the answer to this.
You mean we'll prove something weaker, right?
I guess it's not weaker nor stronger. You're assuming less and you're concluding less. We'll prove both things simultaneously. Yeah, let's just do the proof and we'll see what we got. Okay, so let me, for simplicity, let's fix I equals 1, I guess. So fix I equals 1. So what I mean by this is that I'm assuming my complex is a link HDX. And now assume also that I'm working in the two-dimensional part of the complex. Okay, so assume even that the complex is two-dimensional. So it has vertices, edges, and triangles, and forget about everything else. Okay, and I know that every link is an expander. So what does it mean? It means that I know that for every vertex, think the link around that vertex is an expander. So this is what I know. And my goal will be to prove that this random walk is the same as this random walk. That the random walk on going from the edges down and going from the edges up will be the same. Okay? So okay. So the goal. I want to show that the down-up random walk is the same as the L plus random walk is less than gamma. Okay, maybe gamma prime. Okay, so this is what I want to show. So I'm fixing it for I equals 1. Okay, so now this is really opening up what this means. Okay, so what does it mean? The norm here. Okay, the norm of this operator is the expectation. So it's an operator that works. Both of these are operators. This is also working on level 1. So these are operators that work on the edges, right? So it's expectation over all UV edges in x1. Okay, and then there's two different operators acting on them. One is this L plus, and one is this UD. So it means that for every function from the edges to the reals, so I fix some function, and I need to show that this operator, when it operates on this function, it really shrinks the norm. Okay, so I fix some function on the edges, and I take Actually, no, that's true in my definition, but as I said, because they cancel. Welcome back. Okay. Avi appears. Yes. Okay, so I'm just doing F L1. Yeah, sorry. So I'm doing L1 plus of F at this edge. Okay, let's call it UV minus UD of F at edge UV. Okay, so I just need to analyze this expression. I don't know if you see what is written. So okay. So now the trick is to do this expectation kind of vertex by vertex, but not, the vertices will not be neither U nor V. They will be W. So what we will do is to choose a random edge in this graph in the entire complex. One way to do it is to choose a random vertex and then to choose a random edge in the link of this complex. So I want to write it. So choose a random edge in x1 is the same as choose random vertex in x0 and then choose random edge in, I guess let's call it W, in xw1. So it means the link of this vertex is a graph, and I choose a random edge in this graph. So you see that to make this work also with Weiss, I just need to set the probabilities so that these two things are the same, and that's exactly obtained by defining the distribution on the levels beneath the top level to kind of be induced as marginals from the top, like I said in the beginning. Never mind, if everything is uniform, this is just always going to be uniform, unweighted.
But this procedure, I mean, there might be some edges that are just picked.
Say again?
There might be some edges that are not picked. Like does every edge need to be part of it?
For example, if there's an edge that participates in no triangle, then it will never be in a link, right? But that will not happen if everything is regular here, yes? So definitely we need the complex. Well, we need the complex to be pure. So all the edges come from some one top level, but it doesn't matter. So let's pretend everything is regular, and then this is true. So then I can write this expectation according to this. So it will just be expectation over W, and then expectations over edges in the link of W. Sorry, I want expectation not of an edge in the link of W, but of two neighbors of W, I guess. So, okay, we'll see. Okay, I'll write it here.
But the work is correct. The work is put an edge in x1 in xw1. So it's an edge in the link of W, right? That's how you work. Step 2.
Yeah, but I think I should. I think it's not correct. Choose a random vertex in the link of W. So it's just a random neighbor of W. Yeah, and then that expectation over there, the expectation over there, is just going to be equal to the expectation over W of the expectation over V in the link of W in xw0 of okay, actually I see I'm unprepared for this, so okay, I will do it in a picture because somehow I'm afraid that I will make a mistake. So suppose this is W and I'm looking at the link of W. So I view it as all the neighbors of W are here, and there are some edges between them. Right, so this is the link of W. I guess I want it to be an expander. So every edge here comes from having a triangle touching on W. Okay, so now I want to compare two random walks, but I only look at these random walks over the edges that touch W. Okay, so one random walk is when you just choose one vertex and another vertex independently. Okay, this is like the complete graph if I had here. And the other random walk is the random walk on the link that chooses a vertex and a neighboring vertex. Okay, so one of them is going to be the L plus. It's moving from this edge through a triangle containing W to another edge touching W. That's the L plus. And the other is moving from an edge containing W to another edge containing W, but without any triangle necessarily containing them. Okay, so I guess this is the correct thing. Okay, so I want to say it again. Okay, so I have a function on the edges, and I'm looking at two different random walks on this function. One is moving from an edge to an edge through a triangle, and the other is moving from an edge to another edge, but through a vertex. Right. So this is the the UD random walk, it moves from an edge to another edge, but it goes this way, from an edge down and then back up. And the up-down walk moves from an edge to a triangle and back down. Notice that both of these random walks, even the one that goes up, you can look at the intersection of the two edges, and there's always some W downstairs here. Okay, so all the pairs of edges that move through L plus, there is some this motion is always you can split it into, first choose a random W and then choose a random triangle that contains W and the two other edges. Okay, I don't know if I probably didn't say it correctly. So maybe this will be easier for me to say, that you can choose, so the L plus random walk, you can think of it as you move from an edge to a triangle and then back to an edge. And you can kind of split this walk according to the intersection of the two edges. So you can first choose a vertex for the intersection and then choose two edges that have a triangle between them. So choosing a pair of edges like this is you can, so choosing UV and VW both in, I guess let me call it UW and VW both in a triangle UVW. That's one way to do it. And it's the same as doing choose W and then choose a U containing W and V containing W, not U containing W, U adjacent to W and V adjacent to W, such that UVW is a triangle.
That's because the triangle is unique.
Yes. And it's always going to be the case. You always condition on k minus 2, so you will always have this situation. So you can always kind of decompose this kind of random walk where you have a triangle and two edges in it to a vertex and two edges leaving it so that these two edges make a triangle. Okay? So now you see that the second one, choose W. What is this? Choose U adjacent to W and V adjacent to W such that the UVW is a triangle. This is exactly choosing U and V in the link of W, because these are two neighbors of W, and they need to close a triangle. It means that these guys are adjacent in the link. So it's exactly like choosing W and then choosing an edge in the link. So this is exactly the same thing. So what we have here is that the random walk that goes up can be decomposed into, at every link, you look at the just random walk inside the link. That's in the case of the L plus. Okay, what about the other case, the up-down? So let me do the down-up random walk. So that's even more clear. Well, it's just choose W and then choose U adjacent to W and V adjacent to W with no further constraint, right? It's just what is the down and then up random walk? You can think of it as if first you choose the down where you start and then you choose two neighbors. The triple is the same. Edge, vertex, edge. It's like choosing a vertex and then two neighboring edges. Okay, is this believable? Okay.
Condition on you don't condition on an edge between U and V.
Between,
U and V.
yeah, no condition U adjacent to V. Okay, so that's the difference between this guy and this guy. Okay? Okay, so, all right, so now going back to the analysis, I forgot to do inner product with F. As if the link is complete. As if the link is complete.
It's just a question of whether the link is an expander.
Right. So if the link is a gamma expander, you can imagine that these two things are gamma apart from each other. And when you do this, it's a convex combination of things that are gamma apart from each other, you get gamma. So now I need to write it, but I'm probably going to make a mistake. So let me, you know, if I prepared this properly, it would be like a 2-line thing. So you believe it, and yeah. I mean, really, okay, I can try to do it. Really, what happens is I need to calculate this, I need to do something like expectation of, if you want to analyze the norm of some operator M, you need to do expectation of an edge UV drawn from this M distribution of f of, well, let me do E1, f of E2.
Why don't you just add condition on the fact that the common vertex is W?
Yeah, that's exactly what I'm doing. I say first choose W and then condition. Right, I'm just saying that to analyze this norm, I need to analyze a norm of some graph M. And suppose the nodes of the graph are edges in this case, then I just select a random edge in the graph, and I run f of E1, f of E2, and I compare it to the norm of f, right? And now when I do this with this norm, I need to do it by first choosing W, and then choosing, like Andre is saying, A1 and E2 conditioned on these edges containing W, and again I get f of E1, f of E2. Okay, so this is what I'm doing, and now for the matrix here, I'm writing it for a generic matrix M. Now I need to substitute for M two different things. One is L plus and one is UD. Okay, so when I substitute UD, what I get here is just, what is f of E1, f of E2? Well, if I condition on W, I just need to look at, so if this is W and f is a function on the edges, then I just copy the value of the function on this edge to this vertex. So from f, I get a function on all the vertices in the link of W. And what this is giving me is just the expectation of f squared, because E1 and E2 are independent in UD. So this is one thing that I get. And what I get here is the expectation of f only on the edges in the link. This is exactly what I get in L plus. So I get the expectation of f just on the edges. And the difference between the two is exactly gamma by definition. So, okay, so we get that the link, if you know that there's a bound on the link, you get a bound on the global random walk. Okay. Yes.
So one thing is that this is informative even if you don't have a concept. Just if you have a graph, it says that if you know that there is a bound, that every link, what's a link? It's just a neighborhood of a vertex. If the neighborhood of a vertex is expanding, then the whole enough, there'll be a constant there that will matter. But if then it's expanded. It's a challenge. Build a graph like this. All expanders we know, all expanders you think about are expanders which look like locally like trees. So their link is empty and it's a lousy expander. And it's a highly non-trivial problem by itself just to build an expander graph in which, you know, the neighborhood is even connected. Well, this can be trivially arranged, but you know, if you want the neighborhood of a vertex of every vertex to be expanded, it's star. So this is highly non-trivial, and this is informative anyway. The other thing is, you mentioned it in the beginning, but this is a place probably to stress it, is that this is a local to global condition. You have expanders at every neighborhood, you get expansion. The whole graph is sort of a little unbelievable. So I think you want to say something about the history of this?
I won't have to. What I want to say is the thing that I had hoped to do, and I'm not doing it, is to show now the expander you get from a matroid, not the expander, the complex you get from a matroid, and to look at the links, and you immediately see that the links in any matroid look like multipartite complete graphs. So a link of a matroid, you just kind of, for example, look at spanning trees, you immediately see it. that the link looks like there's a bunch of vertices in different colors, and all the edges are present between every pair of colors. And this kind of graph, if you look at it as a graph, is always, all the spectrum is at most 0. So these guys are 0 link HDXs, and this implies that they're random walk HDXs, and that's how you get the mixing. So you don't need anything more than some inductive arguments like this to analyze this kind of mixing. And next time I'll talk about other applications or other local to global behaviors that these kinds of objects can give us that are useful for PCPs and hopefully also for codes, but yeah, who knows? So that will be next time.